Let's prove that permutation matrices form a group. First of all, we define the set Sn to be the set of permutation matrices. That is the set of all n by n matrices with integer entries, actually 0, 1 entries, that have 1, 1 per column, 1, 1 per row, and zeros elsewhere. This set is known as the symmetric group. So to see that it really is a group, we need to show that it's closed under multiplication, that it has a multiplicative identity, and all the elements have inverses. Maybe let's look at some examples first. When n equals 3, we have the identity matrix. We have matrix 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, and 0, 0, 1, 0, 1, 0, 1, 0, 0, with the ones on the anti-diagonal there. So we have these 6 matrices. These are all of them. It's easy to see that there's 6 because we have 3 choices of where to put the 1 in the first row, and then 2 choices of where to put the 1 in the second row, given that we've already put the 1 somewhere in the first row and we don't want to use the same column again. And then once we've used up 2 columns, there's only 1 place to put the 1 in the third row. So 3 times 2 times 1 is 6. All right, so let's check that permutation matrices are closed under multiplication. So I claim that if A and B are in Sn, then so is the product AB. So to prove this, let's let C be AB. We'll show that C has exactly 1, 1 per row and exactly 1, 1 per column. So to see that C has 1, 1 per row, let's consider row I. Now row I of C comes from taking the dot product of row I of A with all the different columns of B. In row I of A, let's let K be the position of the unique 1. Then there's exactly 1, 1 in row K of B. Let's let J be the column that has a 1 in position K. Or equivalently, if we find the 1, 1 in row K of B, let's let that be in position J. So let J be the unique column of B containing 1 in position K. So then if we take row I of A and an arbitrary column, column J, oops, I guess J is the unique column. If we take an arbitrary column, column L of B, that's going to be 1 if we're looking at column J, because the dot products are, the vectors are going to have 1s in position K both times. So that's 1 if L equals J, and it's going to be 0 otherwise, because all of the other columns of B have that 1 in a different position, not in position K. So if we keep I fixed and let L vary, we're going to go across row I of C, and we've got a 1 exactly once, so we've got zeros n minus 1 times. Now we have to show that C has 1, 1 per column and all zeros. So to see that C has 1, 1 per column and all zeros in the other positions, we can apply the same argument to C transpose. Now, if C equals AB, then C transpose is B transpose A transpose. So namely, we just showed that a permutation matrix, well, a product of two permutation matrices, has exactly 1, 1 per row and all zeros otherwise. Now, if A and B are permutation matrices, so are A transpose and B transpose, because 1, 1 per row here means 1, 1 per column there, and 1, 1 per column here means 1, 1 per row there. So these are permutation matrices, and this product of permutation matrices gives us a matrix that has exactly 1, 1 per row. So row I of C transpose has exactly 1, 1 and n minus 1 zeros. But row I of C transpose is column I of C. So column I of C has 1, 1 and n minus 1 zeros. So therefore C is a permutation matrix. All right, so now that we've shown that the set of permutation matrices is closed under multiplication, we need to show that it has an identity element and that all the elements are invertible. So we claim that Sn has a multiplicative identity element. And that's easy to prove because the identity matrix is a multiplicative identity for matrix multiplication. And it belongs to Sn. it has exactly 1, 1 per row and exactly 1, 1 per column, and zeros everywhere else. So now we need to show that all the elements in Sn, all the permutation matrices, are invertible and that their inverses belong to Sn. So for A in Sn, A inverse exists and belongs to Sn. Well, we can see that the inverse exists because the determinant of A is either going to be plus or minus 1. If we remember, the definition of determinant is a sum of products of matrix entries, 1 per row, 1 per column. Well, there's going to be exactly one way to get a product of matrix entries equal to 1. All the other ways are going to give 0. And that product of matrix entries equal to 1 is going to contribute positive 1 or negative 1 to the determinant. But either way, it's invertible. So that's true by the definition of determinant. All right, so it's invertible, but is its inverse in Sn, or is it just some other matrix outside of Sn? Well, it's in Sn. In fact, the inverse of a permutation matrix A is the transpose. So we claim that A inverse is just A transpose. So to see this, let's consider the product A times A transpose. The ij entry of this product is, I guess, the ith row of A dotted with the jth column of A transpose. So row I of A dotted with column J of A transpose. The column J of A transpose is just row J of A. So it's row I of A dotted with column J of A. Now each of these vectors has exactly 1, 1 in it and all zeros. So row I of A dotted with, I'm sorry, this is row J of A. Row I of A and row J of A are going to dot together. They're going to have ones in different positions if they're different rows. And they're going to have ones in the same position if it's the same row. So this is going to be 1 if I equals J, if we're dotting a row with itself, and 0 otherwise. So in this product matrix A transpose, we've got ones in the diagonal and zeros everywhere else. In other words, A transpose is the identity matrix. So therefore, A transpose, the permutation matrix, is the inverse of A, and the inverses of all the permutation matrices belong to Sn because they too are permutation matrices. So those three claims prove our theorem that Sn, the set of all permutation matrices, is a group. And this is in fact a subgroup of another group that we've studied. Sn is a subgroup of the orthogonal group with integer entries. And it's a subgroup of that because the definition of the orthogonal group is that's all the matrices A such that A transpose equals A inverse. And we know that permutation matrices have that property. So for A in Sn, we have A transpose is A inverse. That's all it takes to be part of the orthogonal group. So permutation matrices form a group, and they form a subgroup of the orthogonal group. The end.